Hello everyone. We are going to do an example problem of an exponential growth problem. So here we have a population of a small town, and the population is going to be growing, as populations tend to do. So we're given here that the population of a certain town is 250 at the start of 2011, and at that time it is estimated that the population is growing at about 6% per year. Okay, so that's all the information that we have. It says write a differential equation to represent this situation and solve it to find the population as a function of time. So if we're going to write a differential equation, if we're going to write any equation, we need some variables, and so we got to define what those variables are. So for a population problem, I'm going to use P because it's nice, it's convenient to have the letters represent certain things and to remember what they are. So P is going to be the population, which is really, number of people. Okay, and it's going to be the population at a certain time, right? And that time is going to be represented by T. So T years after, let's say, January 1st, 2011. Okay. So we want to write a differential equation. So for a differential equation, we need a derivative, dp dt, the rate of change of the population per year, right? Now we have per year, we have 6% per year, right? And we want, if it's going to be dp dt, that's the change in people per year. So the amount of people is given by p. It's 6% of the people per year, so that's 0.06 of the people. So that's going to be people per year. So that's our derivative, and that's our differential equation. Okay, and of course you can separate the variables, divide by p on both sides, and multiply both sides by dt. Okay, and we can integrate both sides and solve for p, and of course the result is going to be our standard exponential growth formula. It's going to be C1 e to the k t, right? And so that's part A, right? We solved it to find population as a function of time. Okay, we got p on one side and no p's over here, just constants and t. Now we have to find those constants, of course, and actually we don't need to. We know what k is, right? K is 0.06. So let me get rid of these and put 0.06 in there instead. Okay, 0.06 t. Okay, we just got to find C1. And of course, we can do that because we know at the beginning of 2001, that's January 1st, 2001. It's been 0 years since January 1st, 2001, and we know that there's 250 people. So we know that P of 0 equals 250. Well, that means we can take this equation and rewrite it with 250 for P, C1 e to the 0.06 times 0, right? 0 times 0.06 is 0, e to the 0 is 1. So that all goes away, and we just get C1 equals 250. So our equation becomes P equals 250 e to the 0.06 t. Okay? And now we can plug that in. This, let's see. This is basically all part A, and this may have been sort of a precursor to part B, but now for part B, we want to find what the population will be in June of 2012. So the question is, what is T at June of 2012? Well, January 1st would be 1 year later, and in June, well, so we can assume it's June 1st, right? That's 6 months later, right? So that's a year and a half, so T is 1.5. So we can go to our calculator, and we can either just type the equation into our calculator, or it's always a good idea to graph it to get a good idea of what it looks like, right? So our equation is 250 times e to the 0.06t, and our calculator is going to use x, but it's just an independent variable. That's okay. So we're only going 1 year, so zoom 6 is going to be fine. Or maybe it's not. It's up at 250. So let's go zoom fit, and then we get a better idea. And let's look at our window. It goes from 137. Let's go down to 0 so we can get a better sense there. And let's go by 50s, or maybe 25s as our scale. And then we can get a good idea. So there's 25, 50. 1, 2, 3, 4, there's 100. 1, 2, 3, 4, there's 200, and 250. So it looks about right at that intercept. And we can just trace at 1.5, and we get our answer to part B, 237.5. Right? So this is population. We can't have a half a person. So we can say, about 200. That rounds up, right? So maybe about 273. So for our answer, we can put about 273. Now, we used our calculator. If we want to show our work, maybe we should say, P of 1.5 equals 250. Pen's not working over here very well. 250 times E to the 0.06 times 1.5. It equals 273 point, what was it? 554, which is approximately 273 people. Okay? This was 272. No, 274 people. That rounds up. There we go. So, okay, 274 people. 273, if you show your work right here and you round down, if you lose any points for that, you're not going to lose much, right? You got the right answer, and, rounding down when it comes to people, not a huge deal, because it's not a big difference. But technically we round up, but not a big deal. Okay, part C. Approximately when should the population reach 300? Well, it's got to be after 1.5 years, because at 1.5 years, it's not quite there yet. We can, of course, trace and get an idea. Maybe it's 3 years. 299, that's pretty close. It ought to be close to 3 years. What we can do, and I'll get a new page here, what we can do is take our equation and say we want to know when P equals, when does P equal 300, right? So we can set P equal to 300 and say that's going to be 250 e to the 0.06 t, and we want to solve for t. So we divide by 250, right? Take the natural log of both sides, so ln of 300 over 250, or you could reduce that to 30 over 25, and then 6/5, right, if you want, 1.2. Equals 0.06 t. And now we divide by 0.6. Or multiply by 0.06, that is, or multiply by 106. So that cancels out. So t equals ln of 1.2, right? 300 over 250 is 1.2, divided by 0.06. So you can just, second quit. You can do ln of, and let's just go ahead and make sure didn't do any math errors there. I can just keep it the way it was because the calculator can do the hard work. Divided by 0.06, and we get 3.03. So our estimate of about 3 years was pretty close. 3.03. And if you want to convert the 0.03 to months or days or whatever, feel free, but no need to. T equals approximately 3.03 years, right? And actually that rounds up as well. So 3.04 years. Okay? And there you have it. All right? And I'll follow up shortly with a exponential decay problem where we're population of something is reducing, is getting smaller. All right? And we'll see you then.